All right, welcome to this next video. In this particular video, we're trying to cover the concept of Newton's method. And in the first part, we'll be approximating solutions to equations. So what Newton's method actually does, it uses the idea that you can find the solution of an equation by approximating it by using an iterative process. And that's what Newton's method is really about. So the whole idea is demonstrated in this picture over here. So what happens is that you choose a particular initial x value. In this case, we'll call it x0. And we apply Newton's formula, which is a iterative process, meaning that we do approximations and we compute it. So we then have to use our calculator for this and keep repeating the process until there's a convergence of some sort. So initially you'll see that we'll pick an actual root within an interval, so x0. And then what we do, it uses the idea that every time you take the tangent at each and every single point, you get closely to getting what the approximate value is. So after you substitute x0 into the formula, which is given to us in our further studies formula sheet, you then go on again and get another x value, and then you plug it back into the equation, gives you the tangent, gives you another value, and then finally we get to x star, which will actually be the actual root that this approaches. So that's how Newton's method works. So we use it to approximate to get solutions. We'll do an example shortly. But what also happens is that there's also failures to this particular method, in that it is a process that helps us get roots fairly quickly, but things can go wrong. So sometimes it might not be able to get the actual solution that we need because of the nature of the way the diagram behaves. So for example, you'll see that sometimes the tangent line does not intersect the x-axis, and therefore we cannot continue with the iterative process. So that's a limitation of Newton's method. And you need to know this because the examiners are always keen to ask how to do that. And then the other approximation will be demonstrated in the diagram is that sometimes if you're not given an interval that is well suited, you'd find that the function has got more than one solution, like this one here. You'll be substituting your x0 there, but like the tangent at that particular point goes to another root that you're trying to find and not the one that you're looking for. So it's quite important that the domain with which you're trying to find your roots that is well specified and you understand exactly what that means. Another one of these approximations is that it fails to find the root entirely, and it leads us to a situation like this particular diagram is showing. So you will see that once you apply the iterative process, you'll see that your solution will keep jumping from one tangent to another. So you'll get x is 0, and then you get x is 1 once you do the process again, and then you get x is 0. So what happens is that this alternates between the 2 points, and sometimes they will say that it is cycling between the 2 points. That means it goes back and forth. Or another term you could use would say that the solution is looping. So it's quite important for us to be able to understand that. And I think it's quite important when using Newton's formula. So this first video is going to be initially longer because I'm really trying to explain the whole thing. And then we could do it with an example. So let's jump right into this one. So here's a question. It says, using Newton's method to approximate the root of this particular function in this intervals 1 and 2, let x0 be 2, and then you're trying to find out what all these alternate roots will be through this iterative process that we're going to do. But before we do that, I just want to explain something. So because this is a normal cubic equation, we are able to just simply use our calculator in order for us to find that particular root. So let's jump right into the calculator now. So what you can do mode on your calculator, and what you want to do, you want to solve an equation of this sort. And you can see with our equation, we'll have 1, we'll have 0 for the next term, and then we will have -3, and then we'll have 1. So once we do this process, we can see that we get a solution which is 1,58 going all the way 86, if you want to round it off to whatever decimal places. So this is the solution that we're looking for because it's between 0 and 1. But that equation would have another root, which is 0,347, and it would have another root. So we are trying to get back to this root. That's what you're trying to do. But remember, you will be faced with questions where the roots are not that easy to find, and therefore you need to work out what the solution is. So luckily for this one, we can actually compute this, but we'll use Newton's method to now verify our solution. So remember, Newton's formula is given to there. So remember that XR, this XR is the initial value that we'll put in, and then we'll do consecutive processes of trying to do that. And remember, it is the function over its derivative. So here we are given what f of x is. We then have to find the derivative of this. And we can clearly see that the derivative will be 3x squared minus 3. So now, in us starting this iterative process, we'll say, okay, if we are trying to find x1, we will substitute x0 plus f of x0 over the derivative of x of 0. And you can see what that looks like. So if we're trying to find this x1 value, our initial value is going to be 2. We're just plugging that into the formula that we have over, we'll then substitute what f of 2 is over the derivative of that, of f of 2. Now let us jump right into trying to find out what the solution looks like. So in this case, you can go x1 equals to 2, and then because of our formula, we can go minus, and this will then be 2 to the 3 minus 3 times 2 plus 1 all over the derivative of that, where you keep on substituting 2. So what we'll then do, if you then just plug this straight into your calculator, you'll see that you will get an approximation of about 1.6666667. And the whole idea that boils down from this is that once you do this, you will then try use x2. But now in x2, you will then substitute your previous solution. So now this becomes f of x1 over the derivative of x1. So what that means is that you will take the previous answer that you've used here, come and compute it and put it back in there. And then once you do that again, you'll get another solution, which is 1.54861111, or like that. So you can use that in your calculator. So now in x3, you'll see that you now have to use the solution that you got at the top, x2 over, and that's why this is called the iterative process. It is a computation that we then have to use. So let's go. You get 1,532390162. You can verify these with your calculator, and then you can go on again and then get the other solution where you can go. Now you have to use your previous solution, x to the 3 over the derivative of x to the 3, and then you can go on and see how this converges. 532088989, and then you can go to the approximation of that, which is going to be, you have to use your previous answer, and therefore you go x to the 4 over the derivative of that. So we can go on through this entire process, and you'll see that it takes slightly longer to do. So what I will then do, you will see that as you keep working with this particular expression, it does get to converge. So you'll see that the solution x, the sixth solution and the fifth solutions are exactly the same. And therefore we say that this has converged to this particular root. And you'll see that this root is exactly the same as the one that we would compute when using our calculator. So the whole process of Newton is to really get to approximate this particular solution. So because this has taken the video to be slightly longer, what I will do, I will redo this question now, and I'll show you a much quicker way on how to compute this on your calculator. So I hope this has made sense, and therefore I will see you in the next video.